Imagine a question so fundamental, so seemingly straightforward, that for centuries, some of humanity's greatest minds really believed it must have an answer. Like a master key to unlock all mathematical truth. A universal method for every logical puzzle. But then, one brilliant mind stepped forward and delivered this devastating proof: no such key exists. What if a universal problem solver, a theoretical machine made of pure logic, revealed not just what was possible, but the inherent limits, the actual boundaries of logic and computation itself? Hey everyone, welcome to the Deep Dive. I'm your host, Alex.
And I'm Jordan. And today, we're not just looking at some dusty old document. We're plunging into what you could call a conceptual earthquake. It's a research paper that, and this is no exaggeration, laid the intellectual groundwork for every single computer you ever used.
Yeah, we're talking about Alan Turing's groundbreaking 1936 paper on computable numbers with an application to the Entscheidungsproblem. Now, that title might sound a bit intimidating, maybe a little academic.
It definitely does.
But its impact is anything but obscure. It's everywhere.
Absolutely. It was received way back on May 28, 1936. But this isn't just some historical artifact we're dusting off. It's genuinely the seminal blueprint for, well, everything from our tiny smart devices to the whole internet infrastructure. And it completely reshaped how we understand what mathematics and, by extension, what machines can actually accomplish.
It really feels like the conceptual birthplace of computer science as we know it.
It really is. Turing didn't just solve a problem. He kind of invented the very tools, the language we use to even think about computation today.
Okay, so to really get the brilliance here, we kind of have to rewind. We need to go back to a very basic but surprisingly slippery question Turing was wrestling with. What does compute even mean? Seriously.
Right. Before this paper, the idea of computable was, well, it was pretty ambiguous, wasn't it?
Yeah, totally informal. It was more intuitive. Like, we'd say, okay, if I can write down the steps for a calculation, then, intuitively I can compute it, like following recipes.
And you have the steps, you can do the thing.
Exactly. But what are those steps? How do you take that very human, slightly fuzzy intuition, that informal idea of just following a procedure, and nail it down? How do you formalize it so it's universally understood, rigorously provable, and just utterly unambiguous?
Mm-hmm. And that's not easy. It's a foundational challenge. It had really stumped some of the brightest minds before Turing came along.
Yeah.
Indeed. And right at the heart of Turing's motivation was this huge mathematical challenge. It was known as the Entscheidungsproblem.
Which is German for?
Decision problem, yeah. This was a question famously posed by the legendary mathematician David Hilbert back in 1928, though it built on his earlier ideas too. Hilbert had this grand vision, this program.
Right, Hilbert's program.
Exactly. He wanted to formalize all of mathematics into one single system that was totally consistent, and crucially decidable. So he asked, can we figure out a general sort of mechanical procedure that if you give it any statement in formal logic, it will tell you definitively if that statement is provable or not?
Okay, let's pause there because the weight of this. You need to picture the intellectual climate back then, early 20th century. Mathematicians had built these incredible structures over centuries, right? Calculus, geometry. But they were searching for this ultimate logical certainty.
Mm-hmm. A solid foundation.
Yeah. Hilbert's dream was basically a universal truth detector for all of math. You feed it any mathematical claim, any logical statement, like, say, are there infinitely many prime numbers, or that famous Goldbach conjecture, is every even integer greater than 2 the sum of 2 primes?
That we still think about.
Right, and this machine, this procedure would just spit out true or false, provable or unprovable, every single time, no ambiguity.
It was the ultimate quest for certainty, a really grand ambition to establish this complete, consistent foundation for all mathematics.
This wasn't just some academic puzzle, it was about bringing absolute, undeniable order to the whole world of mathematical thought, like finding the master algorithm for truth itself.
And that's precisely why nailing down the definition of computable was so absolutely critical. The existing mathematical frameworks, they were incredibly powerful, sophisticated even.
They gave us calculus, advanced algebra.
For sure. But they truly lacked a rigorous, universally accepted definition of what computable or mechanical procedure actually meant. How could you possibly prove that something cannot be done by a machine if you haven't even precisely defined what a machine is, or more broadly, what computation itself is.
Right, you can't set limits on something you haven't defined. It's like trying to measure the edge of a cloud.
Exactly. You need that solid bedrock definition first before you can even start exploring its boundaries, its inherent limitations.
Yeah.
That was the missing piece, the crucial foundation that Turing set out to provide. He wanted a formal definition that could stand up to the toughest logical scrutiny. And context here is important, too. The early 20th century was, well, it was a turbulent time for math. Also incredibly exciting. A period of really profound reevaluation. People were pushing the boundaries of what they thought was possible.
Yeah, like shaking the foundations.
Precisely. Just 5 years before Turing's paper, back in 1931, Kurt Gödel, another absolute giant, had published his groundbreaking incompleteness theorems.
Oh yeah, Gödel. That sent shockwaves, didn't it?
Huge shockwaves.
Yeah.
Those theorems basically demonstrated that within any sufficiently powerful formal system, like any system complex enough to handle basic arithmetic, there will always be true statements that you just cannot prove within that system.
So things could be true, but unprovable using the rules you have.
Exactly. And that was a major fundamental blow to Hilbert's grand program. It shattered that long-held dream of achieving complete mathematical certainty.
Right, and it's really important, I think, to draw a line between Gödel's work and Turing's. They're often mentioned together, but they were tackling slightly different angles of this big challenge, weren't they?
They were, yeah. Gödel's theorems were fundamentally about provability, about what statements could be derived logically from a given set of rules and axioms within a formal system. He showed there are mathematical truths that are just beyond the reach of formal proof, even if they are undeniably true.
So Gödel found limits to proof.
Turing, on the other hand, was tackling something a bit different, though definitely related. What can be calculated or decided by a mechanical process, by an algorithm. He wasn't just showing the limits of what is true or provable, but more profoundly, the inherent limits of what we can algorithmically find out, what a machine can actually do.
Okay, let me try an analogy. Is it like Gödel said, there are true sentences written in a language your rulebook can't fully translate. And Turing said, even if you could translate them, there are some questions your machine, following its rules, can never actually answer or decide.
That's a really good way to put it, yeah. It's a subtle but crucial difference. Gödel focused on the limits of formal systems. Turing focused on the limits of algorithmic processes. One's about truth versus proof, the other is about computability versus uncomputability. And Turing wasn't working in a total vacuum. There were other brilliant minds wrestling with this same idea of effective calculability, like the American mathematician Alonzo Church.
Ah, Church. Lambda calculus, right.
Exactly. Working independently over at Princeton, Church had come up with his own definition for what a calculable function might be. He used this formal system he developed called lambda calculus. Now, without getting too deep into the math weeds,
Please don't.
lambda calculus is basically a different way to express computation. It's based on functions and transformations, rather than the step-by-step actions of a machine.
So less mechanical, more abstract function manipulation.
Sort of, yeah. And remarkably, Church reached similar conclusions to Turing about the Entscheidungsproblem specifically, that it was unsolvable. In fact, Turing's paper even includes a proof showing that his definition of computability using his machine is actually equivalent to Church's effective calculability using lambda calculus.
Wow, okay, so two completely different approaches arrived at the same fundamental conclusion.
Precisely. And that's hugely significant. It showed that these different paths coming from distinct mathematical ideas, one based on a theoretical machine, the other on abstract functions, they converged on the same core concept. It really strengthened the case that they'd hit upon something fundamental about the nature of computation itself. It wasn't just one person's quirky idea. It was a robust, universal truth.
So we had this incredibly rich, but also kind of messy mathematical landscape. Gödel showed unprovable truths. Hilbert asked for this universal decision machine, but nobody even knew how to define mechanical procedure properly. What was desperately needed was, well, a concrete but still abstract model of computation. Something everyone could agree on, something rigorous, something you could actually prove things about, something that separated calculation from the squishy, error-prone human brain.
Right. We needed a definition of computation that was as clear and undeniable as, like, a basic mathematical axiom.
And that's exactly where Turing's paper comes in. He provides this conceptual machine, this framework that could formalize any conceivable mechanical calculation. He basically created a universal language for algorithms.
So how does he do it? Well, Turing starts by laying out his precise definition of computable numbers. He describes them initially as the real numbers whose expressions as a decimal are calculable by finite means.
Okay, that sounds a bit abstract
He
still.
does, but the crucial, really elegant leap he makes right after is to say, quite simply, according to my definition, a number is computable if its decimal can be written down by a machine.
Ah. Okay, so he immediately grounds it. Instead of just finite means, it's what a machine can do. It shifts the focus from human intuition to a mechanical process.
Exactly. It anchors the abstract idea in a tangible, albeit theoretical, mechanism.
Okay, let's unpack this machine then, because when we hear machine today, we think laptops, servers. That's not what Turing meant, right?
And not at all. He wants us to imagine a human computer. And that's literally what they called people who did calculations by hand back then, often in big teams.
Right, rooms full of people with pencils and paper.
Exactly. So imagine you're one of them. You're meticulously writing down numbers on a really long strip of paper. You're following a strict set of instructions, step by step. Maybe you have a pencil, an eraser. You've got limited immediate memory, maybe a few numbers you're keeping track of in your head. And that paper is your external workspace, your scratch pad.
Okay, I can picture that. Tedious work.
Very. So Turing took that human process, tedious, error-prone, and he stripped it down. He distilled it to its absolute bare mechanical essence to create his theoretical computing machine. He was essentially asking, what's the absolute minimum set of capabilities a machine needs to perform any calculation a human could theoretically follow instructions for?
He's stripping away the biology, the intuition, coffee breaks.
Right, getting right down to the logical core of what calculation is. And this theoretical machine, which we now universally call a Turing machine, it has these core components that are remarkably simple, yet incredibly powerful. It's almost minimalist, which is part of its genius.
Okay, what are they?
First, there's the tape. Think of it like an infinitely long scroll of paper, or maybe like a roll of film, divided into individual squares or cells.
Infinite. That's important, isn't it?
Crucial. Each square can hold a single symbol, typically just a 0, a 1, or maybe a blank space. This tape acts as the machine's external memory, its limitless scratch pad. The infinite part is key, theoretically means the machine never runs out of working space. It removes memory capacity as a fundamental limit on computability itself.
So memory size isn't a constraint on what can be computed in theory, only on whether we can build it in practice. That's a big abstraction.
It is. Then second, we have the scanned square. At any single moment, the machine is only directly aware of one specific square on its tape. Just one. That's the scanned square, and it reads the scan symbol on it.
Like a little spotlight moving along the tape?
Exactly like that.
Ah.
A tiny spotlight, focusing its attention with absolute precision. It only sees what's directly under the light, one symbol at a time. This kind of models the limited focus a human calculator would have at any given instant. Okay, third component. The M configurations. These are the machine's internal states of mind. Think of them as M configurations, represented by a finite set of conditions. He might label them Q1, Q2, up to Qn.
States of mind. For a machine.
Well, yeah, metaphorically.
Yeah.
These states let the machine remember what part of the process it's in or what it's supposed to do next without having to write notes all over the tape. It's like different modes or gears a simple robot could be in. Its current state dictates its behavior. He explicitly compares this to a human calculating who can only be in a finite number of mental states at once.
Okay, that makes sense. It's like the machine's internal context or short-term memory, but totally mechanical and finite. Elegant.
Very. And finally, the fourth piece, the rules. This is the machine's program. Its behavior at any moment is completely determined by just two things. Its current mint configuration, its internal state, and the symbol it's currently reading on the scan square.
So state plus symbol equals action.
Exactly. These are its instructions, laid out in a finite table of rules. A typical rule might sound like this. If you are in state Q1 and you see a 0, then write a 1 for on the square, move 1 square to the right on the tape, and switch your internal state to Q2. That's it. A simple lookup table. And the actions the machine can take, the atomic operations, are incredibly basic. It can print a new symbol on the current square, overwriting what's there, erase a symbol, leaving it blank, move the tape head 1 square to the left, move 1 square to the right, or change its internal M configuration, switch state.
That's really it. Just write, erase, move left, move right, change state. No addition, no multiplication.
Nope, not built in. Turing argued that these incredibly simple operations are sufficient. They form the fundamental building blocks. Any complex calculation, like addition or multiplication, or even running complex software today, has to be broken down into a sequence of these unbelievably basic atomic steps.
It's like saying you can build any Lego structure imaginable using only 5 basic brick types.
That's a perfect analogy. That's the power of it.
Yeah.
Now, Turing specifically focuses on what he calls automatic machines, or A machines. In these, every single move is completely dictated by the current state and the symbol being scanned. There's no room for choice, no need for an external operator to step in. It's fully deterministic.
Like clockwork. Given the state and symbol, the next step is fixed.
Precisely. He contrasts these with choice machines, where an external operator might need to make decisions, but for defining computability rigorously, he sticks to the automatic deterministic ones, removes all ambiguity.
Okay. And then within those A machines, there's a specific type he's interested in, right? The computing machines?
Yes, a computing machine is an A machine designed specifically to print out figures, primarily zeros and ones, which form the binary decimal sequence of the number it's supposed to be calculating.
So the output we care about is that sequence of zeros and ones.
Right. The machine might use other symbols on the tape temporarily, like little markers or rough notes to help its process. He calls them symbols to assist the memory. But those are just intermediate steps. The final, meaningful output is the sequence of zeros and ones representing the number. Those other marks can eventually be erased. Now, here's a really crucial distinction Turing makes between circular and circle-free machines. This is absolutely fundamental to whether a number is truly computable in its potentially infinite form.
Circular versus circle-free? Okay, what's the difference?
A circular machine is one that eventually stops printing the important figures, the zeros and ones that make up the number, or it gets stuck in a loop where it keeps moving and maybe changing internal symbols, but it never produces another figure for the actual output sequence. It stops making progress on the number itself.
So it either halts completely or just spins its wheels internally without adding to the final answer.
Exactly. It might be calculating pi, gets a few digits out, and then enters some internal state loop where it just shuffles symbols back and forth forever, but never prints the next digit of pi. That's circular.
Okay, so what's circle-free?
A circle-free machine is the opposite. It just keeps going, printing out figures indefinitely, reliably producing the infinite sequence of the number it's computing. Only the numbers that can be computed by a circle-free machine are the truly computable numbers in Turing's definition. They have infinite decimal expansions that a machine can, in theory, generate forever.
That term circular makes sense then, like it gets stuck running in circles, not moving forward.
It's directly related to the idea of getting stuck in a non-productive loop.
Okay, this is still pretty abstract. Did he give examples in the paper to make it more concrete?
He did. To make it tangible, let's look at his first example, Machine I on page 233. It's designed to compute a really simple sequence, 0, 1, 0, 1, 0. Just alternating zeros and ones forever.
Okay, 0, 1, 0, 1, 0, 1. How does the machine do that?
It's surprisingly simple. It only uses 4 internal states, or M configurations, which Turing labels B, C, E, and F. And there's a small table of rules. Let's walk through it.
All right, let's try. Where does it start?
It starts on a blank tape. In its initial state, configuration B.
Okay, state B sees a blank square. What's the rule?
The rule for B seeing none, a blank, is perform operation P0, print a 0, and then switch to state C.
Got it. So the tape now has a 0 on the first square, and the machine is internally in state C.
Perfect. Now, the machine is in state C. Let's assume it hasn't moved yet, so it might still be scanning that 0, or perhaps the rule implies moving right implicitly, or maybe the next rule handles the move. Let's check the table.
Okay, for state C, if it sees none, meaning it's implicitly moved or is looking at the next blank square, the rule says R, move 1 square right, and stay in state C.
So it just shifts its focus 1 square to the right onto a new blank square, but stays in state C. Right. Now it's in state C and scanning a blank square again. The next rule for state C seeing none is P1, print 1, and move to state E.
Okay, so now the tape has 0 on the first square, 1 on the second square, and the machine is in state E. It's looking like a 1.
Exactly, we're getting there. Now it's in state E, presumably scanning the 1 it just printed, or the blank square next to it. Let's see. The rule for state E seeing none is R, move right, and switch back to state B.
It moved right again onto another blank square, and it's back in state B, the starting state.
Precisely. And now the whole cycle repeats. It's in state B, sees none, prints 0, goes to C, then C sees none, moves right, stays C, sees none again, prints 1, goes to E. Then he sees none, moves right, goes back to B.
And that loop just keeps going forever, laying down 0, 1, 0, 1, 0, 1 on the tape. Wow! That's incredibly simple. Just 4 states and a handful of rules generate an infinite sequence.
It really shows the power of the model. Even this tiny example demonstrates how complex behavior, in this case, generating an infinite sequence, can emerge from incredibly simple deterministic rules. The level of detail shows the rigor he was aiming for. Now, here comes one of the most brilliant insights in the paper, a really crucial step towards everything we think of as modern computing. Turing showed how any Turing machine's entire set of rules, its complete blueprint, its program, can be encoded
Encoded how?
as a standard description, or SD. This SD is just a finite string of symbols using a very specific limited alphabet like A, C, D, L, R, N, and semicolons. Each symbol or sequence represents a part of a rule, like move left or print 0 or go to state Q5.
So you can write down the entire machine's instruction manual as a single string of text.
Essentially, yes. And then this is the really cool part. The string of symbols, the SD, can be converted into a unique number, a description number, or DN. It's usually a single, absolutely massive integer. He shows that you can map each symbol in the SD string to a digit or sequence of digits, creating one giant number that uniquely represents that specific machine.
Okay, wait. You're turning the machine's program into data? A number that represents the entire machine.
Exactly. That's the conceptual leap. It's like digitizing the machine itself. Instead of needing a different physical device for every calculation, you can describe any machine, any calculation, as this sequence of symbols, which then becomes a single number.
That DN is the machine, in a way. It's a perfect numerical representation of its entire behavior. It's like giving every possible computer program its own unique serial number.
You got it. And this isn't just a neat theoretical trick. It has profound consequences.
Which leads us to, I feel like something big is coming.
It is. This leads us to perhaps one of the most profound ideas in all of computer science, the foundation for basically every computer we use. Turing proved it's possible to invent a single machine.
One machine to rule them all.
Ha! Kind of. He called it the Universal Computing Machine, or UTM. And this single machine can compute any computable sequence, any sequence that any other Turing machine can compute.
How can one machine do the job of potentially infinitely many different machines?
By doing exactly what we just discussed. It takes the standard description, that blueprint, the DN of any other computing machine, as its input data.
Whoa. So you feed the universal machine the description number of, say, the machine that calculates pi.
Right. You write the DN of the pi calculating machine onto the UTM's tape.
And then what?
Then the universal machine reads that description number, interprets the instructions encoded within it, and essentially simulates the behavior of the pi calculating machine step by step using its own simple operations. It mimics the machine described by the DN.
So the UTM isn't hardwired for pi or prime numbers or anything specific. It's a simulator, a mimic.
Exactly. It takes another machine's program as its input,
Yeah.
and then it acts like that machine. This is the huge conceptual leap that directly foreshadowed the modern general-purpose computer. Before Turing, computer usually meant a person, or maybe a custom-built adding machine. After Turing, it meant this abstract universal machine capable of performing any calculation as long as you give it the right instructions, the right DN.
Okay, my mind is slightly blown here. So every laptop, every smartphone, every server, it's essentially a physical manifestation of this universal Turing machine concept.
At its core, yes. Think about it. You load different software onto your computer, a word processor, a game, a browser, an AI model. Each piece of software is like a different standard description. Your computer's hardware, the physical UTM, reads that software, the SD, and then behaves like that specific machine, a word processing machine, a gaming machine, whatever.
So this paper, written in 1936 with just theoretical machines on paper, it's the actual blueprint for the entire digital age. The idea that one piece of hardware can run countless pieces of software.
That's pretty much it. It's the theoretical foundation for that entire paradigm of flexible, programmable computing we just take for granted now. It's genuinely remarkable. Turing also spent time showing just how many numbers fall under this definition of computable. He demonstrated that the class of computable numbers is incredibly vast. It includes pretty much every number we actually use in science and engineering.
Like what kinds of numbers?
Well, all algebraic numbers. Those are numbers that are roots of polynomial equations with integer coefficients, think square root of 2, cube root of 5, things like that. You can compute them to any desired accuracy.
Okay, what else?
Also famous transcendental numbers like pi and e. We have algorithms that can calculate their decimal expansions indefinitely, even though they go on forever without repeating. The paper even specifically mentions things like the real parts of the zeros of Bessel functions, which are important in physics, are also computable.
So basically, any number we can practically calculate or define an algorithm for seems to fit.
Pretty much. He argued that essentially any number we naturally regard as computable falls into this category. It supports the intuition he started with, but now it's backed by this rigorous machine definition. And importantly, this class of computable numbers is enumerable.
Enumerable meaning you can list them out. Like there's a first computable number, a second, a third, even though there are infinitely many.
Exactly. You can, in theory, assign a unique positive integer to every single computable number. This comes directly from the fact that every computable number corresponds to a Turing machine, and every Turing machine has a description number, which is an integer.
Okay, so the set of computable numbers is huge, includes almost everything we use, and you can even list them out theoretically. Sounds pretty comprehensive.
It sounds comprehensive, but here's the twist, and it's a profound one. While the class of computable numbers is huge and enumerable, it does not include all definable numbers.
Wait, definable numbers, what does that mean? Numbers you can describe.
Yeah, numbers whose properties you can state clearly and unambiguously using finite mathematical language. You can write down a precise definition. But Turing showed there are numbers you can perfectly define, yet no Turing machine can ever fully calculate their infinite decimal expansion.
Hold on, you can describe it perfectly, know exactly what number it is conceptually, but
Yeah.
no machine, no algorithm can actually churn out its digits forever.
Precisely. It's like having a perfect map to a location, knowing exactly where it is, but being fundamentally unable to ever travel there. Defining something doesn't guarantee you can compute it.
That's weirdly unsettling. So there are mathematical objects we can describe with complete precision, but they are fundamentally beyond the reach of any mechanical calculation.
Yes, there are inherent fundamental limits to what is theoretically calculable, even by an ideal machine with infinite resources. We can talk about them, define them, but we can't compute them. It was a stunning revelation about the limits of algorithms. And this discovery, the existence of uncomputable yet definable numbers, leads directly to the other huge result in the paper. It allows Turing to provide a definitive proof that the Entscheidungsproblem, Hilbert's decision problem, has no solution.
Back to Hilbert's dream of the universal truth detector for math. Turing proved it's impossible.
He did. He proved there is no general mechanical process, no algorithm, no single Turing machine that can take any mathematical statement and decide yes or no whether it's provable within a given formal system. Hilbert's grand vision of complete logical certainty for all of mathematics shattered.
It demonstrates a fundamental boundary, then.
Okay.
A limit to what any algorithm, no matter how clever or powerful, can ever achieve.
Exactly.
Okay, but how? How do you prove something like that can't be done? It seems almost paradoxical. How did he prove such a sweeping negative?
It is clever. He used a technique related to Gödel's work and also work by the logician Georg Cantor, often called a diagonal argument, or proof by contradiction.
Contradiction, so assume the opposite and show it leads to nonsense.
Pretty much.
Yeah.
He says, okay, let's assume for a moment that such a universal truth detector machine does exist. Let's call it machine H. Then, using H, he shows how you could construct a specific, self-referential mathematical statement or paradox.
Like the liar paradox, this statement is false.
Similar in spirit. He constructs a scenario where if machine H says the statement is provable, it leads to a contradiction. And if machine H says the statement is not provable, that also leads to a contradiction. Machine gets trapped. It would have to essentially prove and disprove the same thing or be unable to decide, breaking its own rules.
It's like that classic riddle, the barber who shaves all men in town who don't shave themselves. Who shaves the barber? If he shaves himself, he violates the rule. If he doesn't, he must shave himself according to the rule. The system collapses.
Exactly. That kind of self-referential loop creates a logical impossibility. So because the assumption that machine H exists leads directly to this inescapable paradox, the initial assumption must be false. Therefore, no such universal decision machine can exist. To be a bit more specific about how he connects this to machines, Turing's proof essentially boils down to showing something slightly different, but equivalent is impossible. He demonstrates there's no general algorithm, no Turing machine, that can determine whether any given arbitrary Turing machine will ever halt or be circle-free.
Ah, you mentioned circle-free earlier. That means it keeps computing useful output forever, right? So halting would mean it stops.
Right. Or more generally, will it ever stop running? Or will it run forever? This is famously known now as the halting problem. Can you write a program that looks at any other program in its input and tells you for sure, yes, this program will eventually stop, or no, this program will run forever?
And Turing proved you can't.
Correct. He proved the halting problem is undecidable. There's no universal algorithm that can solve it for all possible programs. And then he showed that if you could solve the halting problem, you could use that ability to solve the Entscheidungsproblem. Since the halting problem is unsolvable, the Entscheidungsproblem must be unsolvable too.
Wow, so the inability to predict if a program will stop running is fundamentally linked to the inability to create a universal truth machine for math.
They are deeply connected. The paper states this pretty directly, showing there's no general process to determine if a machine's description number corresponds to a satisfactory, circle-free machine. And if you can't even determine if a machine will successfully complete its computation or run forever productively, how could you build a master machine to decide the provability of any statement, which might involve simulating machines that never halt?
That undecidability, the halting problem, it still has huge implications today, doesn't it? Like for debugging software.
Oh, absolutely. It means you can never build a perfect general-purpose bug detector that can look at any piece of code and guarantee it won't fall into an infinite loop under some condition. That's a fundamental limit we still live with in software engineering.
Okay, shifting gears slightly. While the paper's incredibly rigorous, did Turing himself acknowledge any, well, maybe limitations or points where he had to rely on intuition?
He did, actually, especially in the initial part where he's justifying why his machine model captures everything we intuitively mean by computable. He admits that his arguments connecting the machine's actions, scanning, writing, changing state, to the actions of a human computer are fundamentally appeals to intuition. He even says they're rather unsatisfactory mathematically for that reason.
So he knew that bridging the gap between the intuitive idea and the formal model involved a step that wasn't purely mathematical proof. Yes. He was essentially saying, look, this model seems to capture everything a human following rules does, and here's why I think so. But he acknowledged it wasn't a formal derivation from axioms. Of course, the model has held up incredibly well, and its equivalence to other formalisms like Church's lambda calculus gives us enormous confidence in it. But it's interesting he noted that initial reliance on intuition, and it's always good to remember, the Turing machine is purely theoretical. It's a logical construct. The paper describes it using these dense tables of symbols and rules. It's not like an engineering blueprint for building a physical device.
Right. It's about the logic of computation, not the electronics.
Exactly. And that level of abstraction can sometimes make it challenging to really grasp the machine aspect without visualizing it or using analogies. But that abstraction is also its greatest strength. It makes the concept universal, applicable to any possible technology that implements computation.
We touched on the halting problem, but it's worth emphasizing again, maybe. That difficulty in knowing if a machine is circle-free seems like a major hurdle highlighted in the paper.
It really is. The paper makes it clear that determining if a given description number represents a satisfactory or circle-free machine is inherently problematic. In simpler terms, given an arbitrary program, you generally can't tell for sure if it will ever halt, or if it will just run forever without finishing its task.
And that's the core of the undecidable halting problem.
And it has those real-world consequences. If you're verifying critical software, say for controlling a power plant or a spacecraft, you can use tools to find many bugs. But you can never have a tool that guarantees finding all possible infinite loops or non-halting conditions. There's always a theoretical possibility of something slipping through because of this fundamental limit.
Okay, and just to be super clear again on Gödel versus Turing, they both found fundamental limits, but they're different kinds of limits, right?
Definitely distinct.
Yeah.
Gödel showed limits to completeness in formal systems. He found there are true statements that simply cannot be proven within the system's rules. The paper mentions this propositions where neither the statement nor its negation is provable. Truths beyond proof.
Okay, limits of proof.
Right. Turing, building on his model of computation, showed limits to decidability. He found there are questions, like the halting problem or the Entscheidungsproblem, that no algorithm, no mechanical procedure can systematically answer for all cases. Problems beyond computation.
Limits of computation. Got it. True, but unprovable. Gödel. Versus undecidable by algorithm. Turing. Both huge, both related, but different flavors of limitation.
Exactly. Both fundamentally challenge Hilbert's program and the dream of complete mathematical certainty, but from different angles.
The paper even throws in another interesting nugget, right? Something about Dedekind's theorem.
Ah, yeah, that's a fascinating point. He briefly mentions that a classic important theorem in real analysis, Dedekind's theorem, which is crucial for defining the real numbers and ensuring there are no gaps on the number line, doesn't actually hold in its standard form if you replace the concept of real numbers everywhere with computable numbers.
Whoa. So the universe of computable numbers has a slightly different structure than the universe of all real numbers, including the uncomputable ones.
It suggests that, yeah, the computable numbers, while dense, might have subtle gaps or structural differences from the full continuum of real numbers that mathematicians usually work with. It implies that restricting ourselves to what's algorithmically possible subtly changes the mathematical landscape itself.
That's a really deep point. The limits of computation aren't just about what we can't do. They might actually change the nature of the mathematical objects we can work with.
It hints at the profound implications of taking computability seriously as a foundational concept. So stepping back, Turing's paper didn't just solve a problem, did it? It basically launched an entire field.
Computer science, yeah.
Absolutely. It gave us the formal definition of an algorithm. It gave us the theoretical model of a the Turing machine and the universal machine. And it established the fundamental limits of what computation can achieve. Modern computing, the whole digital age,
Yeah.
it arguably wouldn't exist in the same way without this paper laying the groundwork.
It provided the conceptual bedrock, the language, the key ideas. Okay, let's dive into our speculative corner then. What if? What if this paper hadn't been written? Or, flip side, what if Hilbert had been right and someone had found a solution to the Entscheidungsproblem? A working truth machine.
Wow. Okay, if the paper hadn't been written, or maybe significantly delayed, would we have developed general-purpose computers as quickly? Or at all in the same way?
Maybe we'd just have lots of specialized calculating machines, like one box for doing taxes, another totally different box for weather forecasting, another for code breaking. No single machine that could do all of them just by loading different instructions.
It's possible. The concept of the universal machine, of software being distinct from hardware, might have taken much longer to emerge. Technological progress could have been way slower, much more fragmented. It's hard to imagine our world without that core idea.
And the other way. If the Entscheidungsproblem was solvable, if there was a master algorithm for mathematical truth,
That would be world-changing. Imagine feeding any mathematical conjecture, Riemann hypothesis, PV, SMP, into a machine and getting a guaranteed provable or not provable answer. It would revolutionize mathematics, maybe even science, if scientific laws could be expressed in that formal logic.
but would it be good? Would it take the creativity out of math? And what about the halting problem? If the Entscheidungsproblem was solvable, the halting problem would have to be too, right?
Yes, the logic follows that way. So we'd be able to perfectly predict if any program would halt. Imagine debugging software then. But it also raises philosophical questions about determinism, maybe even free will if human thought is computational. It gets weird fast.
Okay, back to reality. How do the limits Turing found still shape things today, like AI?
They define the fundamental boundaries for AI. No matter how complex or powerful an AI gets, if it's based on computation as we understand it, running on Turing-equivalent machines, it's still subject to the same limits. It can't solve the halting problem for arbitrary programs, for instance.
So an AI can't build a perfect AI debugger either.
Nope. And it means that questions like, can AI solve any problem a human can formulate, might be answered no if some of those problems are fundamentally uncomputable. It keeps AI grounded in the realm of algorithms, even as it gets incredibly sophisticated at simulating intelligence. Questions about true consciousness or sentience in AI are often debated in light of whether consciousness itself involves non-computable elements.
And his work didn't just define what is computable, but it also paved the way for thinking about how efficiently things can be computed, right? A complexity theory.
Exactly. Once Turing established the baseline of what is theoretically possible, the next logical step was to ask, okay, among the things we can compute, which ones are easy and which ones are hard? This led directly to complexity theory studying the resources, like time and memory, Cape squares, needed to solve problems.
So moving from can it be done to how long will it take or how much memory does it need?
Precisely. Which is crucial for everything from designing efficient algorithms for databases to understanding why encrypting data is secure, because breaking the encryption is believed to be computationally hard. It's about the practical feasibility of computation, building directly on Turing's foundation.
What about quantum computing? Does that change the game? Does it break Turing's limits?
That's a common question. The general consensus among computer scientists is no, not really in terms of what is computable. Quantum computers operate on different physical principles: superposition, entanglement, allowing them to explore many possibilities at once and run algorithms that are incredibly fast for certain specific types of problems, like factoring large numbers, which threatens current encryption.
So they're faster for some computable problems.
Much faster, potentially game-changingly faster for certain classes of problems. But they don't seem to solve problems that are fundamentally uncomputable according to Turing, like the halting problem. They are still considered to be within the theoretical framework of Turing computation, just implemented on a radically different, more powerful physical substrate. They might change the landscape of complexity, what's easy versus hard, but not the ultimate boundary of computability, what's possible versus impossible.
Okay. And the philosophical side. If our brains are essentially computational, like biological Turing machines,
Then our minds, our intelligence, would also be subject to these same fundamental limits. That's the computational theory of mind hypothesis. If it's true, it means there might be concepts or problems that are perfectly well defined, but that the human mind is fundamentally incapable of solving or fully grasping, just like a Turing machine can't solve the halting problem.
so things like creativity, intuition, consciousness, are they just incredibly complex computations, or is there something more, something non-computable happening?
That's one of the deepest questions. Turing's work forces us to confront it. If thinking is just computation, it's limited. If it's more than computation, what is that more? It directly impacts how we see ourselves and our place in the universe.
Okay, so here's a final provocative thought for everyone listening. What if the next great uncomputable problem isn't tucked away in pure mathematics or theoretical computer science? What if it's something closer to home, like fully understanding consciousness, or the ultimate laws of physics, or maybe even the nature of complex systems like societies or ecosystems? Are there fundamental truths about our reality that we can perhaps define or describe, but that no machine, and maybe even our own minds, can ever fully compute or predict?
It definitely makes you wonder about the ultimate limits of knowledge itself, doesn't it? So today we've taken a really deep dive into Alan Turing's absolutely monumental 1936 paper on computable numbers with an application to the Entscheidungsproblem. It's truly a foundational text. It gave us the theoretical computer, the universal machine, and this profound, maybe even humbling insight into the fundamental limits of what algorithms can achieve.
Yeah, it's such a powerful reminder, even now in our age of seemingly limitless technological advance. These fundamental questions and limits that Turing uncovered back in 36 still shape everything. They prompt us to keep rethinking what's truly possible, and maybe what lies fundamentally beyond our algorithmic reach. So what stood out to you listening to this? How does Turing's legacy, these ideas of computability and its limits, resonate with how you see technology, or maybe even the boundaries of knowledge itself? That's all the time we have for this deep dive. I'm your host, Alex.
And I'm Jordan.
Thanks for joining us on the deep dive. We'll catch you next time.